Don't learn to spell from a physics teacher, guys. Okay guys, now we're going to talk a little bit more in depth about cyclotrons. Probably not a heap more in depth, but a little bit more in depth. So we all know, hopefully by now, that a cyclotron is something that can fit on a tabletop, and it's a particle accelerator. So it doesn't do relativistic speeds like the LHC, because that's a little bit too challenging to manage. But they can get stuff moving pretty bloody quick. So between the two Ds, so here's one, here's the other, between these two Ds we set up a potential difference. Now remember, potential differences and charged particles, so let's duck back over to here real quick. We have a positive plate and a negative plate, so we can set up an electric field between these two things. This electric field provides the electric force, and we end up doing work on these charged particles. When we do work on something, or work is done by a particle, it's relating to its energy. So if I take something that's at, let's do 100 volts, 0 volts, and I'm going to let a proton go from here. So a proton will have work done on it by that field, and the field will accelerate that proton. It will speed up as it moves through that field. The amount of work done by it is 100 electron volts. That 100 electron volts is kind of like gravity acting downwards on the proton. Similarly, if I had a proton here with 100 electron volts worth of energy, it would make it just to this top plate and then stop and run out of energy, just like going up against gravity. So when we have a cyclotron, like this one here, I'll do green particles this time. When we have a cyclotron, what we're going to do is have a positive charge just here, and I'm going to pretend that my bottom plate is now positive. So we've got the flippy upside down version of this. So now my charged particle is going to race towards that top plate. The field is doing work on it. Now as soon as that charged particle enters this magnetic field here, this sort of idea is going to take over. We use the right hand rule, thumb points in the direction of conventional current, fingers point in the direction of the magnetic field, and we can find out pretty quickly that this particle will actually have, well, that's terrible, it will move in a semicircular path, just like, sort of like this, around that D shape there. While it's in this D, it's got a magnetic field acting on it. It's out of the electric field. There are no electric fields above that plate or below this one here. So it's not going to be able to speed up or slow down while it's in the Ds. It will only ever change direction. So the magnetic field produces a centripetal force on it. It goes through a uniform circular motion, doesn't speed it up, doesn't slow it down. All it does is gives it an orbital path, I guess, or a circular path. And the whole point of that is so that it can be reinserted into this field, which is now swapped about. And the top plate is now positive. The proton, let's do a hydrogen ion, because that is a proton, enters here and has worked on it by the field, speeds up. Now when it gets to the bottom plate now, it goes, same deal, right hand rule, it goes into this field, but because it's going a little bit faster because of the work done, it's a little bit bigger circle. Comes back to here, and as you guessed it, we've swapped around again. So you can kind of see what happens here. Every time it goes through the electric field, it has work done on it by the electric field. Every time it goes through the magnetic field, it basically goes in a circular orbit, and so on, until our particle has just the right amount of energy, and we run it into a sample of some description. So let's say that's our sample, and we're making that hydrogen ion ram into it. And what we're doing is taking something that's moving, so something's moving really, really fast, which means that it's got lots of kinetic energy, which means that it can interact with and overcome large electric fields. Now, if this sample here was something like nitrogen's number 7, I think. So let's say it's nitrogen, and let's say nitrogen's number 7. It's got 7 protons in its nucleus. This, our positive test charge, or our hydrogen ion, doesn't want to run into that thing. It's got a really big repulsive force on it. Every time we get a little bit closer, remember, Q1, Q2, and R squared. Every time we get closer, we're actually, half as far away, so twice as close, means 4 times the force. If we're a tenth the radius, now we're 100 times the force. So it needs a lot of energy to overcome this repulsive force. Repulsive. Wow, that's terrible. Don't learn to spell from a physics teacher, guys. Repel these ions from interacting with it, which is why we need something like a cyclotron, so we can make things go around in circles really fast, build up work as we cross this D each time. So if we have, let's go 10,000 volts of potential difference, and we cross that gap, let's say we do 50 crossings at 10,000 each, we've got 50,000 times 10, 500,000 electron volts worth of energy. I think that'll work. We've got all of this potential energy to overcome this electrostatic repulsive force. If we've gone through the electric field 50 times, remember we go through once here, we go through a semicircle, we go through once here, go through a semicircle once here, so we're actually going through 2 times per lap, so this would actually equal 25 orbits, 25 laps. And we can calculate the radius that it's going at using some of the equations in the last video. R is mv on qb, k is q squared r squared b squared on 2m, etc, etc. So we can actually work out the maximum kinetic energy this particle will have at a certain radius and a certain field depending on its charge to mass ratio, or we can work out its radius depending on its momentum and charge ratio. Alright, so really light particles, really big charges like electrons will go in incredibly small orbits. The beauty about a system like this is even if impurities get injected into here, it's only certain particles that will go at a certain radius and will actually be able to make it through this gap. Everything too heavy won't be able to accelerate across the gap fast enough. Anything too light is going in too much of a small circle. So you only really end up with the sample of, let's say, nitrogen being impacted by our hydrogen ions. It's only that stuff that'll actually make it there. So we can, have some very unique things that we desire to hit it, and they're the only ones that'll actually make it through. So cyclotrons are really great. They use the projectile nature of charges in electric fields and the circular motion nature of charges in magnetic fields to make something incredibly valuable and incredibly useful to medical diagnostics and the production of radioisotopes everywhere.